Okay, hi everybody. We're continuing our discussion of the first law of thermodynamics, and today we'll talk about enthalpy. In the last video, I talked about this equation here, QV equals delta U. Essentially, this is a statement that the change in internal energy is equal to the heat that is transferred at constant volume. And this guy, CV, the constant volume heat capacity, would allow me to relate that heat transferred to a change in temperature. This all looks well and good, but there's this giant problem. And here it is. Heat is a path variable. This equation only applies if the volume is constant. Well, guess what? There is a whole lot of chemistry which does not occur at constant volume. And let me give you one example. Let's talk about the electrolysis of water. So imagine I have water behind some piston. H2O liquid. And I'm going to electrolyze it. That is, take H2O liquid and make H2 gas plus 1/2 O2 gas. Well, those gases are a lot less dense than the liquid. So if I do that process, my piston is going to expand. Here I'll have H2 gas plus O2 gas. And when that piston expands, because I form those gases, it has to do work, right? The system has to do work. And so lots of chemistry does not occur at constant volume. What we would really like is an equation which would relate the heat transferred at constant pressure to temperature changes. Lots of chemistry occurs at constant pressure. It's out on the benchtop, open air. So if I had something which would relate constant pressure changes, that would be really useful. Luckily, we don't have to figure this out. The guys who figured this out are right here, Rudolf Clausius and William Gibbs. You may have heard of Gibbs. We'll talk about him later, as in Gibbs energy. And what they said we should do is think about a new variable, which they called enthalpy, H, given the symbol H. And it's defined as follows. H equals U plus PV, where U is the internal energy, P is pressure, and V is volume. Why did they do this? Let me show you. I'm going to take a derivative of this expression, a general differential. And if I do that, I get something like dH equals du plus, this is a product rule, I'm multiplying pressure times volume. So you take the derivative of the first and leave the second constant, that's V dP, plus derivative of the second and leave the first constant, P dV. I'm now going to substitute in an expression for du from the first law of thermodynamics. So I can say that du is equal to dq plus dw, heat plus work. And now I'm going to substitute in my expression for work. Remember from last time, I can write a differential expression for work, which is minus P dV. This term will cancel with this term. I'm left with dq plus vdp. And if I put a limitation on here that I'm talking about constant pressure, I get something which looks like this. dH equals dqp. I'll point out that this derivation is not mathematically rigorous. These aren't exact differentials, so I technically can't do this. If you took it to the math department, they'd be unhappy with me. But this communicates the central important idea, which is this, right? Delta H is equal to QP. In other words, the heat which is released or absorbed by a physical process or a chemical reaction which occurs at constant pressure is equal to the change in enthalpy. Enthalpy will allow me to relate heat transfers at constant pressure. In general, H is different than the internal energy because some of the energy which is transferred at constant pressure is used to do work. In the example that I just gave you, I have to put in more energy to expand the gas, right, in the electrolysis of water. So in general, H is different than the internal energy because of the first law of thermodynamics. Some heat can be used to do work. Some things that you should note about enthalpy. It is an energy, has units of energy like joules. It is formally an extensive variable. We'll also talk about the intensive version of the enthalpy, the molar enthalpy, would have units of joule per mole. H is a state variable. All of these variables, U, pressure, volume, they're all state variables. Therefore, H is a state variable. If you tell me the state of the system, I can tell you what its enthalpy is. And last but not least, and this is important, you might ask about the temperature dependence. Remember that for an ideal gas, the internal energy is only temperature dependent. It will turn out that enthalpy is not solely temperature dependent. It can depend on other functions. But there are important cases where it is temperature independent. It only depends on temperature. Right? We'll talk about some of that in the coming weeks. Okay. In the case of internal energy, we have the constant volume heat capacity, and we define an analogous quantity called the constant pressure heat capacity, CP. I can already see a mistake in my notes, so here I'm going to fix this. This should say CP. There you go. So constant pressure heat capacity, it's defined in complete analogy to the constant volume heat capacity. Specifically, Cp equals the partial of H with respect to T at constant P. Or if I rearrange that, I get this version of it. dH equals Cp dt. Cp describes the instantaneous change in enthalpy with respect to temperature when pressure is held constant. So it's the slope of these plots. And if we knew what that slope was, if we knew what Cp is, we could calculate delta U, Q, W, and delta H. I should put this on there. One more correction. What's this? So we could calculate everything. Cp is also formally an extensive variable. Twice as much stuff would take twice as much heat to achieve some temperature change. And so there is a molar constant pressure heat capacity, Cp, simply the Cp divided by N. And this is sort of the million-dollar question at this point. How do I get Cp? Right? How does Cp compare to Cv for an ideal gas? In other words, if I heated a gas at constant pressure to achieve some temperature change, would it take more heat, less heat, or the same amount of heat compared to the same temperature change at constant volume? Pause the video for a second and think about that. If I heated a gas up at constant pressure, would it take more energy, more heat, less heat, or the same amount of heat to achieve some temperature change compared to heating it at constant volume? Pause for a second, think about it, and then come back and talk to me. Welcome back. Here's the answer. It will take more heat when I heat the gas at constant pressure. And here's why. If I have the condition that pressure is constant, the gases can expand. I'm not requiring the volume to stay constant. They can expand. And that means that they're doing work. Right? Work costs it energy. So you have to transfer more energy in the form of heat per unit temperature change, and that corresponds to a larger heat capacity. All right, I'm going to give you a mathematical equation to derive this, and if you don't like the derivations, check in here in a second. Here we go. H equals U plus PV. I want to take the derivative of this expression with respect to temperature when pressure is held constant. And that looks something like this. The partial of H with respect to T when pressure is held constant is equal to the partial in U with respect to T when pressure is held constant, plus this product, pressure times volume, would be a product rule, except for the fact that I'm holding pressure constant. When you see this subscript P, it means pressure is held constant. And if that is true, then I can simply leave that as a constant, and I get the partial of V with respect to T when pressure is held constant. All right, a couple of things. The first is this. Remember that for an ideal gas, U only depends on temperature. That means that it doesn't matter if I hold pressure constant or I hold volume constant. They're the same, okay? And this, you'll remember from before, is CV. The other thing is this guy. If I solve for volume for an ideal gas, I get something which looks like this. Oh, stop. nRT over P. If I take the partial derivative of this with respect to temperature, when pressure is held constant, I get this, nR over P. Plugging all of this in, the partial of H with respect to T at constant pressure, this is what we just defined as CP. CP equals, this was CV plus pressure times nR over P, cancel, cancel, equals CV plus nR. My phone's ringing. Here's what this result tells me, right? The constant pressure heat capacity is greater than the constant volume heat capacity for an ideal gas. And it's greater by 1 unit of the ideal gas constant. This is exactly what we had predicted and what we'd expect from this analysis. In summary, we've defined a new variable, enthalpy, H. H equals U plus PV. Enthalpy has the important characteristic that the change in enthalpy is equal to the heat which is transferred at constant pressure. Delta H equals QP. And in terms of the molar amount, CPM minus CVM is equal to R. Right? The constant pressure heat capacity is greater than the constant volume heat capacity for an ideal gas. All right, I'm going to stop here and we'll talk about adiabatic changes next time.